Bismillahirrahmanirrahim. Assalamu alaikum, dear students. I'm Arif and I welcome you all in today's session. To access the notebook for today's session, you can access course page on my personal website arifbhat.me. The other way is to download all the notebook files from course GitHub account ArifPUCIT, and all the notebooks for this course are housed in this public data science repository. Well, this is the Jupyter Notebook dashboard running locally on my machine at port 8888. And here is the notebook for lecture number 6.21 of the 6th module, Machine Learning, for the course titled Tools and Techniques for Data Science. In the last session, we started with our discussion of our first classification algorithm, that is logistic regression. This is the second session on logistic regression, and if you have not watched the previous session, I strongly recommend that you should watch that first and then fall back to this for a better understanding. Let us move on to the agenda for today's session. My dear students, I will start with a recap of previous session where we discussed logistic regression using a single layer perceptron. Then I will move step by step to arrive at the error or loss function that we can use for logistic regression. And unlike linear regression, which use sum of squared errors, logistic regression use cross entropy loss, also known as log loss function. After that, we will see as to how we can use our friendly gradient descent algorithm to find the minima of this loss function. And after giving you all the conceptual knowledge, we will then implement the gradient descent algorithm to find the decision boundary on a synthetic dataset. I will also use Scikit-Learn's logistic regression model to draw the decision boundary on the same dataset. And finally, we will compare the results of the two models. We have a lot to do today, so let's start playing. My dear students, let us start with a quick recap of previous session of logistic regression before I move ahead. Well, logistic regression is a supervised machine learning classification algorithm that is mostly used for binary classification. Well, the upper portion of this image shows the working of a perceptron, which is a basic computational unit of a neural network that is designed to perform binary classification of input vectors. Well, these input values or feature vector is fed into the perceptron. Each input feature has an associated weight, which determines the contribution of that input feature in the final output. And this bias at the very top, represented by W0 over here, is a constant term that allows the perceptron to adjust the decision boundary. This summation unit over here, shown in green, computes the sum of the dot product of the two vectors, weights, and the feature values. The output of this summation unit is represented by Z, which will be a scalar value and can be in the range of -infinity to +infinity. In the previous session, we used the step function and sigmoid function as the activation function, which convert or map this real value of Z to the predicted value of Y hat. Well, for binary classification, we normally assign a value of 1 to say a positive class and a value of 0 to say negative class. In case of a step function, which is not shown over here, if the value of Z is positive, we map it to class 1, that is Y hat equals 1. And if the value of Z is negative, we map it to class 0, that is Y hat equals 0. On the contrary, The sigmoid or logistic function maps this real value of z in the range of 0 and 1 using this sigmoid function. Note this table showing different values of z from -10 to +10 and the corresponding sigmoid values. I have also plotted these values for better visualization. We have z along the horizontal axis while sigmoid of z along the vertical axis. This range of z can vary, of course, from -infinity on the left to positive infinity on the right. But right now it is ranging from -10 to +10. My dear students, you can see in this table as well as in the graph, if z is a very large positive value, sigma of z approaches to 1. So for 10, sigma of z is 0.999. On the contrary, if z is a very large negative number, sigma of z approaches to a value of 0.0. You see, for -10, sigma of z is 0.000045. Moreover, if z is exactly 0, its sigmoid is exactly 0.5. So the value of sigmoid for a specific data point can be interpreted as the probability of that data point of belonging to a specific class. If we set the threshold to 0.5, anything above it over here belong to a positive class and anything over here belong to a negative class. More on this probability thing in later part of today's session, and for the time being let me revise the algorithm that we discussed in the previous lecture to learn the weights of the model. Well, the algorithm is shown over here. Given a dataset, we have m features and say n observations, and each observation belong to either class 1 or 0. The algorithm starts by assigning some random values to the weights vector. Epochs is the number of iterations, which is set to say 100 or maybe 1000, and the learning rate is set to say 0.01, and these are the hyperparameters of our model. In each iteration of the loop, we pick up a data point or observation at random from the positive or negative region that is belonging to either class 1 or class 0. And this line 5 is actually where the magic is happening, that is, the weights are being updated. Well, in case of a step function for a correctly classified point, this yi minus yi hat will be 0. So this second term becomes 0 and no update occurs. However, in case of misclassified point, this yi minus yi hat will either be a positive one or a negative one, so weights will be updated. In case of sigmoid function, my dear students, since this y hat will be a value between 0 and 1, therefore this yi minus yi hat will never be 0. So an update will occur for both correctly as well as incorrectly classified point. And we also saw in the previous session that the correctly classified point will push the decision boundary, while incorrectly classified point will pull the decision boundary with appropriate magnitude depending on its distance from the decision boundary. And finally, this graph over here in the bottom left shows the data points belonging to two classes along with 3 different decision boundaries. Well, this red line was the decision boundary that we achieved using the step function. This brown line, this one, is a bit improved decision boundary that we achieved using the sigmoid function. And finally, this black line is the decision boundary that we achieved using Scikit-Learn's logistic regression model. Now, the question on which I closed the previous lecture was, why our algorithm is not giving the same result as Scikit-Learn? Well, the reason is because of this line 4 of our algorithm. So every time in each iteration, we are picking a point at random. So every time you run this algorithm, you will get a bit different decision boundary. And my dear friends, we all know that this is not the way machine learning works. In machine learning, we find a loss or error or cost function that quantitatively computes the magnitude of our model's error with respect to the ground truth. In case of linear regression, the sum of squared error was a loss function, and we used gradient descent to find the minimum of the loss function and the corresponding regression coefficients. So let's move ahead and first find out the loss or error function that we can use for logistic regression. And after that, we will see as how we can use gradient descent to find its minimum and the corresponding weights. Okay. Oh, well, my dear students, before you move ahead, please pause the video and test your concepts by solving these two questions using paper, pencil and calculator. I have given the hints and I hope that you will be able to do that. And do read this out, that what will happen if we keep the threshold to 0.5, greater than 0.5 or maybe less than 0.5. Okay, after this comprehensive recap of the last lecture, let's move ahead and find out the loss or cost or error function for logistic regression. Consider these 4 observations or data points in this upper scatter chart that belong to 2 classes. These 2 green stars belong to class 1, while these 2 blue circles belong to class 0. Now these 2 scatter charts below show 2 models. Model 1 having a decision boundary shown with the purple color, and model 2 having a decision boundary shown with red line. My dear students, if I ask you which is the right model that classifies the data points into 2 classes, of course you will say this right one. That is model 2 with red decision boundary, where both the green points are in the positive region of this line and both the blue points are in the negative region. Simple. Let me make it a bit complex. My dear friends, now can you tell me which is a better model out of these 2? Well, both models are actually correctly classifying these 4 data points. But intuitively, you will say that probably this right model with red decision boundary seems better, because it is having almost equal margin towards both classes, and therefore will give better results on unseen or testing data as well. Now a $100 question is how to find the answer to this question mathematically, as there can be infinite many decision boundaries or lines that can correctly classify these 4 data points. Well, the answer lies in the loss or error function. And today we will discuss 2 loss functions. First is the maximum likelihood estimate and then binary cross entropy. Okay. My dear friends, before I explain these 2 loss functions, let me describe again as to how we can interpret the output of sigmoid function as probability. Well, given input feature vector and weight vector, we can calculate this z, and then this sigmoid function will map the real value of z between a value between 0 and 1. The value of y hat can be considered as probability of this particular data point to belonging to a class. Now once again consider this scatter plot having 4 data points and this decision boundary. Consider this data point number 1, this green star. We have its feature vector x and the output label y, which says that it belongs to class 1. Suppose we also know the weight vector, which is graphically represented by this red line. And suppose we compute z and then pass it to sigmoid function, and somehow we get a value of this 0.8. This means the model predict that there is 80% chance that this data point 1 belongs to class 1. Similarly, consider this data point 2 now, and somehow we get a y hat or probability of 0.9. This means the model, this red line, the model predict that there is 90% chance that this data point 2 belongs to class 1. My dear friends, if we know the probability of these 2 green points of belonging to class 1, which are 0.8 and 0.9, then the probability of these 2 points of belonging to class 0 will naturally be 0.2 and 0.1 respectively. I hope this makes sense to you all. Now consider this data point 3 shown with this blue circle. We have its feature vector x and the output label y, which says that it belongs to class 0. Suppose then we compute y hat, it comes out to be 0.75. This is a hypothetical value. I have just written it. This means the model predict that there is 75% chance that this data point 3 belongs to class 0. Similarly, if you consider this data point 4 and somehow we get a y hat of or probability of 0.8, this means that the model predict that there is a 80% chance that this data point belongs to class 0. Once again, my dear friends, these are just hypothetical values of y hat which I have written over here. So if you are given x and w, you can actually calculate these. One point that I've kept in mind while assigning these hypothetical probabilities to these data point is if a point lies on this red line, it will have a probability of 0.5, of course. And as the distance of a point increase from this line in the correct region, that is the positive region, its probability also increases. My dear friends, do not move ahead if these concepts are not clear to you. Rewind this part and watch again. I think the background is set now, and now we can move ahead and understand maximum likelihood estimate and binary cross entropy. Well, maximum likelihood estimation is a technique used for estimating the parameters of a given probability distribution using some observed data. Well, consider a dataset having 4 data points or observation with their input features as well as their output labels of belonging to either class 1 or class 0. And suppose the green points belong to class 1 while the blue points belong to class 0. This image is showing 2 models, a model on the left and the model on the right, that classify these 4 points into 2 classes. I have already described the probabilities which this model 2 have predicted or computed. Let me describe the probabilities of this model 1. Well, this green point above the line belong to class 1 because y is equal to 1. This point is on the positive region, so it is correctly classified. On the contrary, this green point below the line, it also belongs to class 1 as the ground label y is 1. However, this point is in the negative region, so it is misclassified. Remember, my dear students, in case of misclassified points, we will consider 1 minus y hat and not y hat, which can be computed by, of course, 1 minus sigmoid of wx. Similarly, this blue point below the line belong to class 0 as the ground label y is 0. This point is in the negative region, so it is correctly classified. Hence, I have computed simply y hat. And finally, this blue point above the line belong to class 0 because the ground label y is 0. However, this point is in the positive region, so it is misclassified. And to compute its probability, we will have to consider 1 minus y hat and not y hat. My dear students, now based on the probabilities that these two models have assigned to the 4 data points, we can find out which is the better model out of these two. Let's compute the maximum likelihood for these two models, which is equal to the product of probabilities of all the data points. Once again, remember, for incorrectly classified point, consider 1 minus y hat. So maximum likelihood for model 1 comes out to be 0.0784, and for model 2 it is 0.432. And since model 2 has higher value of maximum likelihood, so it proves to be better. And visually you can see that model 2 is a correct model. Well, the limitation of maximum likelihood is that we need to compute the product of very small numbers at times. And for a very large data set having tens of thousands of data points, we have to take the product of thousands of very small numbers, which will be a very, very small value. Moreover, finally comparing two such very small values is of course pointless. And the solution is, instead of taking the product, we do a sum. So we convert this product to a summation. My dear students, this takes us to what is known as binary cross entropy. The summation of negative logarithms of maximum likelihood is called cross entropy. So the sum of logarithms of maximum likelihood for model 1 comes out to be minus 2.5459. These are just the same values for model 1. We have just taken the log. Since the log of any number between 0 and 1 is negative, so to make the result positive, we take summation of negative logarithms. So I have put a negative sign with each log, and finally I have arrived to a positive value, that is 2.545. Okay, for model 1 the cross entropy is 2.54, and for model 2 the cross entropy is 0.839. I hope this is making sense. My dear students, in maximum likelihood we select the model having the largest value, that is, we maximize. On the contrary, in case of cross entropy, we select the model having the smallest value, that is, we minimize. And since model 2 has a smaller value of cross entropy, that is 0.839, so it is better. The same result as we have achieved over here. I hope this makes sense. Okay, my dear students, I think I have set the stage right to describe the loss or error or cost function that is commonly used for logistic regression and also for neural networks. It is called cross entropy loss or negative negative log likelihood. We all know that a cost function actually tells us how well our model is performing. That is how close the model's prediction are to the actual output. And in linear regression, we used mean squared error as the cost function, as shown over here where my mouse is hovering, which when plotted on a graph gives us, of course, a convex function. Finding the optimal solution using gradient descent of a convex function is of course possible, and that we have done probably in lecture number 6.4. However, in logistic regression, since y hat is equal to the sigmoid of wx, so using this MSE or loss function for logistic regression might give a wavy a non-convex graph as shown over here. So you can see that there are a lot of local minima. Therefore, finding an optimal solution using gradient descent is not possible. So that means we cannot use this loss function for logistic regression because this y hat is now the sigmoid function, and this will result a graph something like this having many local minima. Therefore, we use a logarithmic function to represent the cost of logistic regression, which is guaranteed to be convex, thus allowing us to run the gradient descent algorithm. Well, when dealing with a binary classification problem, the logarithmic cost of error depends on the value of y. You see, in these two equations, if y equals 1, the cost is minus log of y hat, and for y is equal to 0, the cost can be written as negative log of 1 minus y hat. So these is also shown over here in these two graphs. Well, this left graph is for y equals 1, which shows that the cost approaches to 0 over here when y hat approaches to 1. So over here we have the cost as 0. Similarly, this right graph is for y equals 0, which shows that the cost approaches to 0 when y hat approaches to 0. I hope this makes sense to you all. So this two lines can be written in one line like this: minus y log of y hat minus 1 minus y times log of 1 minus y hat. And this is for one observation, and for n observations we can take a summation and divide by n to take the mean. So this formula shown in green is the formula of cross entropy loss, also known as the log loss error. Well, my dear students, remember, instead of calculating the logarithm of corrected probabilities, we are taking log of y hat, which is the probability of belonging to class 1 over here, the first term, and log of 1 minus y hat, which is the probability of belonging to class 0. When the observation belongs to class 1, that is this y equals 1, so this second term will become 0. 1 minus 1 will be 0. And the formula becomes log of y hat. On the contrary, when the observation belongs to class 0, that is y equals 0, so this first term becomes 0 and the formula becomes simply log of 1 minus y hat. So far, so good. Now we need to find out those values of weights for which this log function, this loss or error function, gives us the minimum value. Okay. My dear students, we did a scuba dive in gradient descent algorithm during our session of linear regression. I think it was video lecture number 6.4. If you are completely new to this algorithm, I recommend that you should watch that video for complete understanding. Anyways, a gradient descent is the first order iterative optimization algorithm for finding a local minimum of a differentiable function. For logistic regression, the cost function is the cross entropy loss shown in green over here. You can see the predicted value y hat is equal to actually the sigmoid of z, and while this z is the sum of the dot product of the weight vector w and the input feature vector for a specific observation. So this is the final cross entropy loss function, this third line. So now the task is to figure out as how we can minimize this jw as a function of w so that we can actually fit the parameters to our training set. So we do this using gradient descent algorithm. Well, the template for gradient descent is shown in red over here. If we have m input features, we will have m plus 1 weights. And to minimize our cost function, we repeatedly update each weight by updating it as itself minus the learning rate times the derivative term, where learning rate eta is a hyperparameter, and if you keep its value too high, the updates will be in large steps. If the value of learning rate is too small, the updates will be in small steps and it may take too long to get to the maximum. Or you may not even reach to the minimum if this repeat loop is running for small number of times. Well, now if you have taken the calculus course, you can easily take the derivative of this jw and can simplify it to this. As soon I will show you this, how we can take the derivative of this cross entropy function and come up to this expression. Soon I will show you this. But for the time being, I am just plugging this derivative of the loss function into this equation, which is shown in magenta color over here now. My dear students, now if you compare this update equation with what we did in gradient descent for linear regression, you will be surprised to realize that this update equation is almost the same. The only difference is the way we compute this y hat. And for linear regression, it is the sum of the dot product of coefficients and feature vector, while for logistic regression, it is sigmoid of z. So far, so good. My dear students, before I move on to implementing this in Python, let me spend few minutes on this cross entropy function and finding out the derivative of it. And since we will be requiring the derivative of sigmoid function to calculate the derivative of cross entropy loss function, so let's differentiate this first. Well, the sigmoid function is shown in red over here, which is equal to 1 over 1 plus e raised to the power of z. In equation 1, I am bringing the denominator up with the power of minus 1 now. Please keep following my mouse, which is hovering over these lines which I am describing. Then we apply the power rule of differentiation in equation 2. In this equation 3, we have applied the sum rule of differentiation. In this equation 4, we have used the constant rule, so this becomes 0. derivative of 1 becomes 0. And for the derivative of this exponent term, we take the term out, multiply it with the derivative of its power. And finally, in this equation 5, I have written it as a product of two terms over here in equation 6. In 5, this is just a simplification. Okay, I think you are with me up till this equation 6. In equation 7, I have added and subtracted a 1 in the numerator of the second term. And finally, I have just done some simplification, and I have finally arrived onto this equation number 8. So the derivative of sigmoid function with respect to z is equal to the sigmoid of z times 1 minus sigmoid of z. And this is shown in magenta color over here. And I think I have discussed the graph of sigmoid function in the very start of the lecture. Over here, I've also shown the graphical representation of the derivative of sigmoid as well. Please do write the Python code to create these two graphs of different z values. My dear students, for crystal clear understanding, I strongly recommend that you should perform this derivation using a paper pencil. And let me move ahead now. My dear students, now I think we are ready to do the derivation of the cross entropy loss or log loss function. I will give you a walkthrough to all the derivation steps, but I strongly recommend once again that you should do it using paper pencil for complete understanding. Well, this loss function j is shown in red, and we need to differentiate it with respect to the weights w, so we need to do partial derivatives. Well, in this equation 1, you can observe that there are just two terms now which we need to differentiate. The first is y times log of y hat, and the second is 1 minus y times log of 1 minus y hat. Well, I have differentiated these two terms separately over here, one on the left and one on the right. Please just keep a map. So this is the first term, y log of y. So I am doing the partial differentiation of this term over here in the left. And this is the second term, 1 minus y times log of 1 minus y hat. And this differentiation is done over here on the right. Okay. Well, let me describe the left part first. The y term over here where my mouse is hovering do not have a w, so it is treated as constant, so it can come out over here. And we know the derivative of log x is equal to 1 over x times derivative of x. So applying this rule over here, we get y times 1 over y hat times the partial derivative of y hat with respect to w. And plugging a y hat is equal to sigmoid of wx, we will come up to this equation. Now we have just a while ago we have computed the derivative of sigmoid, which is equal to the sigmoid function times 1 minus sigmoid function. So we by plugging in to these equation, we get equation like this over here where my mouse is hovering right now. Then there are some simplification steps. So after simplifying, we arrive at the derivative of this left term, which is y dot 1 minus y hat dot x. I hope this makes sense. My dear friends, in the similar fashion, you can differentiate the second term of the log loss function, which I have done on the right side. And with all these comments, I think you will be able to understand this. And finally, you will come up to this derivation will come up to minus y hat dot 1 minus y dot x. Let me just move ahead and plug these values of these two derivatives shown in magenta color to the log loss function. So once we plug in these values, we come up to this equation 2, which is shown over here. And rest is the simplification. I think you will be able to do that. And finally, the derivative of the log loss function is shown in red over here at the bottom. My dear students, once again, for clear understanding, do it using paper pencil. It will be a piece of cake. I have kept written all the steps, so it will not be an issue for you. Okay, I think now implementing this logistic regression using gradient descent will be a piece of cake for you. But I have prepared the cake myself, so if you want to eat it, stay for just 5 more minutes. So let me quickly walk you through this code, which is almost the same that we discussed in our previous session, Logistic Regression Part 1. This code cell is generating a synthetic random dataset using the make classification method of datasets module of Scikit-Learn. N samples is equal to 100, means we want 100 observations or data points. N features is equal to 2, means we want 2 input features for per sample. And classes is equal to 2, means we want all points to either belong to class 1 or class 0. And all the parameters are exactly the same that we used to generate the dataset in our previous lecture. Even this random state, which is 41, I've kept it the same for reproducibility. Let me just execute this. And you see the shape of input features in X is 100 by 2, and the output label Y containing the ground truth is also contains 100 values. Let me show you the contents of these two arrays. Let me just show you the X array. Let me just show you the first 5 rows from the 0th index to 4th index. Okay, and let me show you the entire Y. I hope this makes sense. Let us now visualize the dataset using a scatter plot. Note the scatter method, where I am keeping the 0th column of X along horizontal axis and first column of X along the vertical axis. Let me just execute. Great. Same data points, blue and green, same locations, having same separation among the points of the two classes. Okay, now let us train, but this time using the gradient descent algorithm. Note the update equation. I have written it again. It is shown in magenta color, which we have discussed in detail in our today's session. Well, this gradient descent function is almost the same as the Perceptron function, which I have shown below it, with a bit difference in the line where we are actually updating the weights. I think only this line is different in these two functions. Let me put the lines on. Well, this line 2 of the gradient descent function is using the insert method of NumPy to insert an additional column at index 0, all having a value of 1. And this line 3 is actually initializing the weights vector with values of all 1. Note the weights vector has m plus 1 elements, where m is the number of input features. And of course, in this case, weights will be an array having just 3 ones. Then I am setting the hyperparameters, learning rate to 0.1 and epochs to 10,000. Well, inside the loop, note just the update equation, which is the same as shown in magenta color above over here. You can map it. And finally, when the loop ends, this function returns the bias, which is there at the 0th index of the weights vector, and the coefficients corresponding to each input feature. Let me just execute this cell. Okay, so the code cell has just the definition of sigmoid function, so nothing happens. So This code cell contains the definition of gradient descent, which is of course using the sigmoid function. I need to define the sigmoid function as well. Over here I am defining the sigmoid function, and in this code cell I am actually calling the gradient descent by passing it the x and y, and of course printing the bias and weights. Great. Note, since we have just two input features, so we have two weights, W1 and W2, and this is the bias. Now let us use these weights to plot the decision boundary, which is a line in our case. And to plot the line, we need slope and y-intercept. And the slope m is equal to negative W1 over W2. And this y-intercept b is equal to negative W0 over W1. Well, these two lines are actually generating 100 x and y points to draw the line. Then I'm using the plot method to plot the line, and this scatter method to plot the data points. Let me just execute the code of this cell. Great. So this red line is the decision boundary that we have drawn using the gradient descent method, and this is of course is a good separation of these two classes. Now one last thing is that we want to compare this decision boundary with the one that is given to us using the Scikit-Learn's logistic regression model. So let's move ahead. Okay, so after the imports, I am just creating an instance of the logistic regression model. Let me show you its help page. So the help page of logistic regression is now over here. Okay, fine. The penalty parameter is set to L2. The default value of penalty is L2. My dear friends, this penalty parameter actually specifies the regularization you want to apply. The default is L2, that is ridge penalty. It has other hyperparameters as well, which we will discuss in some future session. But for the time being, I have used true. That is, I have set penalty equals none and solver is equal to SAG. The solver is actually the algorithm to use in optimization. And since I want to compare results of this logistic regression model with my basic vanilla flavor gradient descent algorithm, so I am not doing any optimization. Okay, fine. So after creating the instance of the logistic regression, I am calling the fit method on this model instance by passing it the x and y. Now we have the trained model whose intercept is there in the intercept underscore attribute of the model, and the coefficients are there in the COEF underscore attribute of the model. From these I can easily compute the slope and the y-intercept. Rest of the code is same. Just note that I am plotting both the decision boundaries. Well, the decision boundary for my gradient descent algorithm is in red color, while the decision boundary of Scikit-Learn is in black color. Let me just execute this code again and show you the graph. Great job done. See, the two lines are overlapping now. So our gradient descent algorithm is almost giving us the same decision boundary as given by the Scikit-Learn's logistic regression model. So that is all for today's session, my dear students. I hope it was informative for you all. If you have liked it, please subscribe my YouTube channel and share it with your friends. I wish you all the best. Happy learning and Allah Hafiz.